Hi, my name is Matt Tobin, and today's lecture is on alternative reactor concepts. So, as a reminder, why do we need to confine plasma? Plasma likes to move around and doesn't like to stay in the same place. But if we actually want to make a reactor out of a fusion power plant, we need to achieve a high triple product. As a reminder, the triple product is the product of the density, the temperature, and the confinement time, or how long the plasma is kept in one place. So we need to achieve all of these three, but some of the concepts that we'll talk about today prioritize more increasing the pressure, which is the product of density and temperature, whereas others try to prioritize the confinement time, so reaching higher amounts of time that the plasma is kept in one place. So as a reminder of plasma motion in magnetic fields, remember that plasma, or charged particles in the plasma like to travel along magnetic field lines. And this is due to the Lorentz force. The forces that the particle feels in a magnetic field will keep it moving in a circle, so perpendicular to the B field, and any movement along the B field won't be constrained or affected. So that'll keep these particles moving kind of in helices, in circular paths along the magnetic field lines. This is described, again, we talked about this in the plasma dynamics lecture, this is described using the Lowell radius, which is the ratio of the perpendicular velocity to the cyclotron frequency. So we talked a little bit about accelerators, just touched on them briefly in the tokamaks lecture. So I'll mention them, mention the parts that we talked about before, and then do a deeper dive into accelerators. So recall that in a tokamak is a toroidal chamber that confines plasma. There are plans to use tokamaks both for short timescales and for long timescales. And we use magnets to create the toroidal field lines, so those go around the long way of the donut. And then we also use shaping coils to make the cross-section of the donut not exactly circular. But in order to actually get a twist to the magnetic field line, which is needed in order to counteract the drifts that will tend to move particles outside of the confined region of the plasma, we add a current, which is depicted in this diagram with red lines. And that plasma current twists the magnetic field lines in the colloidal direction, so it gives them a component that points around the short way of the donut, which then allows the plasma, all the particles of the plasma to sample all the magnetic field strengths, which then keeps the plasma better confined. We said that there's another way to create this twisted magnetic field structure, and that's with actually twisting the magnets themselves. And this is the approach that accelerators take. So you can see a few examples of some accelerator coils here. In the case of a accelerator, you don't now need the plasma current, which is great because the plasma current can be a source of a lot of instabilities that can cause disruptions or other unwanted effects in your plasma. Accelerators are more complicated to build because of these twisted coils, but they have kind of some fewer operational problems compared to tokamaks. So you can see a few examples here of twisted coils or some unique designs. The bottom left picture here that I'm standing in front of is the view from the inside of the CNT accelerator, which is at Columbia and is currently undergoing an upgrade. So the accelerator coils are typically difficult to build because they have this interesting twisted geometry. So you can see a diagram here of the coil set of a accelerator kind of unwrapped. So you can see the toroidal field coils going vertically up and down in this diagram, and then the helical coils, which are in light blue in the diagram on the top right of the slide, that twist kind of transverse to them or oblique to them. So one of the ways that we can improve the manufacturability of accelerators is with modular coils. And modular coils, rather than dividing the toroidal field coil and helical field coil set into two different groups of coils, make one set of coils that have these complicated shapes that create the overall same effect of the pair of toroidal and helical field coils. And in this diagram, right above my head, you can see that that's depicted in this kind of S-shaped coil. So the solid lines, again, are the toroidal and helical coils in a typical accelerator, and then in a modular coil accelerator, we kind of take the shaded region, turn that into a coil, and then add those together. And you can see the result in the diagram at the bottom right of the slide, showing the decomposition of the toroidal and helical coils into the modular coils. And this kind of plays into the different classifications of stellarators. So we call the traditional stellarator that has the toroidal and helical field sets a torsitron. A heliac uses also just planar coils, but it actually moves the coils around the magnetic axis in order to create the twist for the stellarator field. And then a helias is what we call the device that uses modular coils, which again creates the same field, but uses these oddly shaped sets of coils to produce it in a more manufacturable way. So one of the big fields that's achieved a lot of attention in recent years with stellarators is stellarator optimization. So in stellarators, the uneven field that can be created by imperfections in the magnetic field, again, due to manufacturing imprecision or poor optimization of the field itself, you can get these pockets of kind of lower magnetic field, and in those pockets, particles can get trapped and then leak out essentially of the confinement device. So the way that we kind of optimize against this, or try to create a magnetic field that has a level of symmetry, basically, that keeps these pockets out of our device, is using quasi-symmetry. So quasi meaning almost, and the term quasi-symmetry indicates that even though we're not toroidally symmetric in the way that a tokamak is, if you take a certain set of coordinates or look at your device from a certain perspective, then you do kind of recover a level of symmetry that helps the field not have these pockets of low strength that leads to particles leaking out. So this idea was proposed in 1986, but even to this day, even the last few years, computational tools are still kind of advancing to the point that they need to be at in order to kind of really take full advantage of this idea. So there's been a lot of work, even in the last 5 years, to create highly optimized stellarators under certain conditions, optimizing for different metrics of confinement or stability to create the kind of optimal stellarator. There are different ways that we can create that symmetry. You can use helical symmetry, axial symmetry, colloidal symmetry. These just indicate that if you unwrap the coordinates, so basically the orientation that you're looking at your field lines in different ways, you recover different types of symmetry. You can see that kind of in the plots at the bottom of this page, showing that when you unwrap the field lines, you get kind of symmetry either diagonally in a helically symmetric stellarator, horizontally in an axially symmetric stellarator, or vertically in a colloidally symmetric stellarator. So a little bit of history on stellarators. The concept was proposed by Lyman Spitzer in 1951 at the Princeton Plasma Physics Laboratory. It was the first US fusion concept. The tokamak was an idea that had been thrown around even in the US at the time, but it was thought to be way too unstable to support such a large plasma current in a magnetic fusion device. So the kind of focus of the research in the US was on stellarators. This was until 1968 when the tokamak was shown to have superior confinement based on experiments in Russia. And because of that, a lot of the funding in the US and even in other places around the world was poured into tokamaks and went away from stellarators. So there's still a lot of research going on in the stellarator community, but this is why kind of tokamaks have advanced so much more and have achieved so much more funding, is because they showed early on that they had much better performance. A quick summary of some of the similarities and differences between stellarators and tokamaks. So tokamaks create an axisymmetric toroidal field using a set of coils. The stellarators create a helical field, usually with modular coils nowadays, but that could be achieved with a toroidal coil set and helical coil set. So in tokamaks, this means that we use a central solenoid to induce a toroidal current in the plasma to twist the field lines. In stellarators, the same effect is achieved with complex and expensive twisted coils. The drawback of the spec in stellarators is that it leads to current-driven instabilities and disruptions, and they can be harder to run in steady state, partially because you actually have to pump in the energy essentially into the plasma in order to sustain that plasma current throughout the discharge. Stellarators, on the other hand, are inherently steady state, so this means that they don't have the same disruptions that tokamaks have and they seem to have looser stability limits in general compared to tokamak plasmas. However, because of the difficulty of optimizing these very complex magnetic fields in accelerators, they tend to perform worse historically than tokamaks. Tokamaks are relatively easy to build and less expensive to build, and their symmetric orbits tend to lead to better confinement. And an additional kind of element of this is that tokamaks, because that helical field is created by the current in the plasma, and that current in the plasma is something that you can adjust in real time, they tend to be more flexible. Whereas stellarators, because the magnetic field is created by all of the hardware that you've already constructed and spent money on, it's harder to change the magnetic field as dynamically as you can in a tokamak. So the kind of leading stellarator experiment in the world right now is the Mittelstein 7X, which is in Greifswald, Germany. You can see a mock-up of the device here. You can see the different coil sets in red and orange. Again, you have the modular coils in red that have these kind of twisty shapes, and then the additional coils in orange that add to the field, but with planar coils. And on the right of the slide here, you can see a comparison of the triple product achievements over the years with these different concepts. You can compare the tokamak concept in the red line, and you can see that because it achieved kind of earlier funding and more attention in research, it was able to achieve higher triple products earlier on. But in the green line, you can see that the kind of stellarator lineage has started to achieve similar triple products, and just because of the lower funding has just lagged a little bit in the tokamak development. Here's a link that'll be included in the description to a 3D stellarator model so that you can get kind of a handle on the different components and look around at different angles on your own. Another major device that is being used to advance the stellarator concept is the large helical device, which is in Japan. You can see again a mock-up of the device above my head. This device is cool because it's a torsatron, so rather than using the modular coils that are used in W7X, it uses these helical coils that have this very cool shape if you look at the device from the inside, which you can see in the pictures on the right. So you can see the twisting of the coils, again, creating that helical field that helps the plasma maintain better confinement. Unfortunately, this device was built earlier on before optimization methods advanced to the level that they are today. So this device isn't as optimized as W7X, but still contributes to stellarator research nonetheless. Highlighting one private company that's working on the stellarator concept. So Thea Energy is taking a different approach to making the helical field that's produced by coils in the stellarator. Instead of using helical coils or modular coils, they have their typical toroidal field coil set, and then they actually use small so-called picture frame coils that act as pixels to the magnetic field all around the torus of the device. And these magnetic field coils can be adjusted individually in real time in order to adjust the magnetic field in a very controlled way. And you can see I've highlighted here in green one coil set where if you energize, helical coil sets around the diameter or around the circumference of the device, you can get a helical field much the same as you would get with a helical set of magnetic field coils. This is similar to using a permanent magnet-based magnetic confinement concept. There are permanent magnet stellarators that have been conceived of and built, typically on smaller scales, but this picture frame coil allows kind of a greater scale up to the device to a power plant level. So that covers the kind of two main concepts that are being studied right now as candidates for fusion pilot plants. We'll talk now about some of the more off the beaten path concepts. These concepts have, histories as long as the stellarator and the tokamak. Again, though, historically they've tended to produce lower performance numbers and therefore just accumulated less funding and therefore developed more slowly over time. However, we've highlighted in these slides several companies that are working on advancing these concepts to see if they can actually provide a path to a fusion power plant at a different scale. So let's start again thinking about the motivation for confining plasma. So again, if you have a perpendicular, or if you have a B field here that goes across the page, the plasma's perpendicular motion is going to be confined, again, because the charged particles in the plasma will tend to travel along the magnetic field lines. So whereas without the magnetic field, the plasma would just expand and cool down. With this magnetic field, its motion is constrained along the field lines, and it'll move along the edges. Now, when we built a tokamak, what we did was we took the ends of that magnetic field and wrapped it around on itself. And in doing so, the plasma now kind of moves in a circle. It doesn't, it'll kind of stay confined. We then talked about how we need to add the helical twist to the field because of the drifts in the plasma. The drawbacks of this whole approach of twisting bringing the magnetic field ends to touch each other into a circle is that, again, you get these drifts. Also, you have big, expensive magnets that you need to build. So one alternative approach to solving this problem of confining the plasma is, what if we could confine the parallel motion, so again, the motion along the field lines, without having to wrap the field lines in a circle? Then you would avoid the curvature drift and the E cross B drift and the other drifts that lead to a loss of confinement in a tokamak. So this motivates the magnetic mirror concept. So a magnetic mirror basically creates a magnetic bottle, which confines the plasma axially along the field lines without wrapping it into a circle. And you can see a mock-up of the magnetic mirror concept here. So you have typically a weaker magnetic field in the center of the magnetic mirror, and then you create a strong magnetic field kind of on the two ends that serve to reflect particles that are moving towards the end of the device back to the center. This is called the magnetic mirror effect. And you can see a mock-up of kind of one particle's motion here above my head. So you can see a particle incoming will experience a force towards, just as it's moving, it'll experience a force that kind of shrinks its gyro orbit, so shrinks the radius of curvature of the orbit that's executing to the point where it actually stops its parallel motion along the field lines if the magnetic field is strong enough, and then reflects and bounces back in the direction that it came. The plasma is in this way confined in the center of a magnetic mirror region. Magnetic mirrors exist in nature as well. You can see in the planetary magnetospheres that the magnetic field lines come closer together near the north and south poles of planets and are farther apart near the equator. And charged particles in the ionosphere of planets actually bounce back and forth between these regions of high field due to the same effect, the magnetic mirror effect, that confines plasma particles in a magnetic mirror. And you can see that the confinement in these magnetic mirrors, both in planetary natural settings and in the laboratory, is not perfect. If you look at the map, for example, above my head, of the incident radiation on Earth of charged particles, so you can see that near the poles, so near the North Pole and the South Pole, the strength of radiation becomes much higher, and that's from these charged particles essentially leaking out along the magnetic field lines and impacting the Earth where, around the north and south poles. Whereas, around the equator where the magnetic field is weak, the charged particles kind of stay away and don't impact the Earth as much. So again, the drawbacks of using this concept is that these very high energy particles, especially ones that are traveling close to closely parallel to the field lines, will not be confined. And through collisions with other particles, as those particles that are higher energy and more parallel to the field lines leak out, eventually other particles will collide and gain higher energy, or become more parallel to the field lines and leak out as well. So over time, all the particles will essentially leak out of the magnetic mirror. So you have to either confine your plasma for longer in other ways, or you can just have a high enough pressure that you're getting enough fusion energy in that time that your plasma is confined. These concepts, plasmas, also experience interchange instabilities in them. This is due to high pressure gradients, where you have a high temperature, high density plasma closer to the axis of your magnetic mirror that then decreases, the pressure decreases as you move radially outwards, and you get kind of a almost like a fluting effect along the column of plasma in your magnetic mirror as your higher pressure particles kind of exchange with the lower energy particles on the periphery. So even in spite of that the confinement difficulties and stability difficulties of magnetic mirrors, there are corporations that are pursuing magnetic mirror concepts for fusion power plants. One of those is Reactor Fusion, which is building a device called WAM that's meant to demonstrate kind of the path to their hammer device. This concept relies on the magnetic mirror kind of strategy for confining plasma. And they kind of improve on the confinement of a basic magnetic mirror, both by using very strong magnets and by applying electric fields to electrostatically confine charged particles in the main region of the plasma. They also use those electric fields to improve the stability of the plasma, which can protect against the interchange instabilities that I mentioned on the last slide. Okay, so that covers magnetic mirrors. Now we're going to talk a little bit about pinches and the pinch effect. So let's motivate the study of pinches quickly. So plasma, just like any matter, will keep accelerating as long as there's a force on it. This is described by Newton's laws of motion. So if we want to keep a plasma in place, we need to look for configurations in which the force on the plasma overall is zero. So how do we compute the net force on the plasma? We talked about this a few lectures ago in the plasma dynamics lecture. We can use, if we're using the fluid description of the plasma, the momentum equation. And if we set the force on the plasma in this equation equal to zero, we can see what configurations in different geometries satisfy this equation, satisfy force being equal to zero, and then build concepts that kind of mimic that geometry. So this is that momentum equation that we talked about in the previous lecture. This kind of describes the motion of the plasma, where the left side, the net force is equal to the mass times the acceleration of the plasma, and the right side of the equation is the sum of the other forces on the plasma. Here, P stands for the pressure, and again, this is just using single fluid magnetohydrodynamics, or the single fluid picture of plasma. So say we want to set the force on the plasma equal to zero, that means we can set the left hand of this equation equal to zero. Say we're looking for a situation in which we don't have any electric field, just keep it simple. We can set the E quantity equal to zero. We're going to say that we don't have any other forces just for simplicity, so ignoring gravity, which is relatively weak on the plasma compared to the electromagnetic force. Again, ignoring collisions because we're just looking at a single fluid picture. So setting all those quantities equal to zero, what we end up with is an equation that says that the gradient in P, so the delta symbol that's upside down of P is equal to J cross B, where J is the current in the plasma, and that's equal to the charge in the plasma times its velocity. So you can see that all in the slide above me. The pressure defined as the product of the density and the temperature, and the gradient in the quantity nt is equal to J cross B. So we want solutions that will satisfy essentially this equation. So just to kind of give an overview, so we've done a force balance on the plasma. The gradient in the pressure, that's the left hand of this equation, is essentially the force that's pushing the plasma outwards. So if you are confining your plasma, for example, in a cylinder, if you have a high pressure on axis, that pressure in your plasma is going to push the plasma to expand outwards, just like it would a gas. Contrary to a gas, though, in a plasma, we have moving charged particles that can carry currents. We have interactions with magnetic fields. So if we have the current going in one direction and the magnetic field going perpendicular to that, the force that will be experienced by the plasma will be felt in the direction perpendicular to both of those, J, the current, and the plasma, or and the magnetic field. The magnetic fields, I'll make a note here, can arise either due to the plasma itself, or it can arise due to external magnets that we apply a magnetic field on the plasma for. So we're going to consider cylindrically symmetrical configurations just for simplicity. Yeah, the issue with kind of these approaches is that plasma will leak out at the end. And this means that approaches like this tend to be pulsed for fusion. So again, if the plasma is leaking out of the end, you can only confine it for so long, and you hope that enough fusion happens in that time that you confine the plasma that you can recover enough energy to repeat the process while still gaining net energy. So the first type of pinch that we'll talk about is the Z-pinch. So a Z-pinch describes a plasma configuration in which we have, in a cylindrically symmetric system, a plasma current, again, that's indicated by the variable J, that's moving in the axial direction, so along the Z coordinate if we have a typical coordinate system, hence the name Z-pinch. And in this case, the pressure which we want to have the highest, or the plasma pressure which we want to be the highest on axis, is going to be pushing radially outwards. So that means that the gradient of the pressure, the gradient of the product density times temperature, is going to be in the R direction, the radial direction. So in order to satisfy this, having a pressure gradient in the radial direction and a current J in the Z direction, we need to have a magnetic field that goes in the theta direction, or toroidally around the axis in our cylinder plasma. So when we do that, we end up with this thing called a Z-pinch. You can see a mock-up on the bottom right of the slide showing when you confine a plasma in this configuration, it kind of keeps the plasma closer to the axis. Unfortunately, there are instabilities that can arise due to this confinement method. One of those is the sausage instability, which is an axisymmetric instability in which you have axially along your cylinder of plasma inconsistencies in the strength of the magnetic field that create a kind of sausage effect in your plasma that pinches closer in some areas and expands the plasma out farther in other areas. And when this happens, you can deconfine your plasma and lose the confinement that you need in order to make a fusion reactor. There's also the King's instability, which occurs when not axially along your plasma column, but azimuthally around the column, you have inconsistencies in the strength of the magnetic field. And this causes the column to get kind of wonky or kinky. We'll show in this video what that looks like in an actual plasma, how a column of plasma can accumulate a kink instability that then causes the plasma to deconfine. So there are companies that are using pinches in order to produce potential fusion reactors. One of those is Zap Energy, which is using a Z-pinch fusion reactor concept. This concept, like again most pinches, prioritizes pressure or the product of NT over tau in trying to achieve a high triple product. And in this case, and in this sense, we consider this a pulsed reactor. So you run the reactor for a little bit of time, it then deconfines, you get your energy from it, and then you can run the reactor for another pulse. Again, kind of accumulating more energy over time over all the different pulses. Their approach at Zap Energy is to build smaller, simple reactors. So these can serve kind of smaller grids, smaller sets of energy customers, as opposed to a giant power plant that can replace a coal or gas-fired power plant nowadays. So we'll show this video that goes over the concept that Zap Energy is kind of studying, so that you can see a Z-pinch in action. So that covers Z-pinches. Now we'll talk about theta pinches. So in a theta pinch, as you might expect, the current in the plasma, rather than running in the axial or Z direction in your cylinder of plasma, is now going to run in the azimuthal or theta direction. When this happens, again, in order to balance the radial pressure gradient in your plasma, you need to create a magnetic field that then goes in the Z direction, or axially along the axis of the plasma. In this case, you end up with a plasma that's typically more stable. However, it can experience a wobble motion, again, kind of similar to the kink instability that we saw with Z-pinches. One approach that we have taken is to combine the Z-pinch and theta pinch approaches into what's called a screw pinch, which has both an axial component and a theta component to the magnetic field. And in this case, that then starts to look a lot like a choke back, where we have kind of a helical field that runs along your cylinder plasma. The only thing that you need then in order to convert that screw pinch into a tokamak is to again take the two ends of your cylinder of plasma and connect them, so you have a donut rather than a cylinder of plasma. You can see a mock-up here of an example circuit that can be used to make a theta pinch of plasma. So again, creating a magnetic field that goes axially. In this case, you can do that using the currents in the plasma itself. So running your azimuthal current using these coils outside of your plasma. So now we're going to combine some of the concepts that we've talked about up to this point, namely the magnetic mirror and the theta pinch. So if we combine these two concepts, we can end up with something that's called a field reverse configuration, or FRC. So we're going to, again, go back to our MHD single fluid equilibrium, again, saying that the gradient in the pressure, which again is the product of density N and temperature capital T, and set that equal to J cross B. So again, this is a force-free equilibrium. We're saying that we want to create a scenario in which we don't have forces acting on the plasma so that it can stay in place. And when we write out, when we use Maxwell equations, we can convert that equation into what you see at the top of this slide. Now, say we want to create a magnetic field that is so strong that it actually reverses on axis. And in this case, that means that it would look like a sigmoid function if you plot it versus the radial coordinate. So I just prescribed basically a magnetic field that we want to achieve, which I'll motivate later. And if we plug that B on the second equation line in this slide into the equation on the first line in the slide, we can pull out what the J and the P are that will allow us to achieve this force-free equilibrium on our plasma. So here I've just plotted what that would look like. In this case, in black on the graph above me, you can see that the magnetic field in black starts at some value, kind of radially outside the plasma, and then as you move towards the axis, reverses fully to the negative value that is at the same absolute value. And then I've again just plotted the value of J and value of P that we get on the previous slide on the same graph, and you can see that it has this kind of double hump structure that peaks a little outside of the axis. I've also created this kind of mock-up that shows, if you're looking side on to this plasma, where the currents and magnetic fields would be in your cylinder of plasma. And again, this is all achieved using the radial pressure balancing the J cross B force of the plasma. So what we do then, once we have kind of this reverse field on axis, is that we can put that plasma in a magnetic mirror. And what that does is it pinches off the field on the sides. It creates a stronger magnetic field on the two ends that, using the magnetic mirror effect, will improve the confinement. And what this does is it actually closes the magnetic field line. So whereas on the previous slide, you could see that in the plot to the top right of the slide, you can see that there are magnetic field lines going in one direction on the outside, then they go on the opposite direction on the inside, and in the original direction, again on the outside. You can actually connect the field lines in the middle such that you end up with these closed field line structures. And this is what characterizes an FRC. The magnetic mirror field that we embed this plasma in then also allows us to control the position of this closed field line object that is the kind of confined plasma. In terms of forming an FRC, one of the most common ways to do it today is using pulse power to quickly reverse an axial field that's embedded in a cylinder of plasma. And you can see those stages kind of outlined here on the right side of the slide. This approach is currently used by Helion and by TAE in order to form two FRCs using this method. And then they actually collide the FRCs formed by this method to heat up the plasma and create a larger amount of plasma that's trapped. So I'll show a quick video from TAE that shows their formation process and how they end up with an FRC at the end. So just to touch on some of the similarities between tokamaks and FRCs, so you can see that on the left side of the slide, right above me, there is a mock-up of half of the spark stellarator, or the spark tokamak, and on the right side of the slide, far right side of the slide is that diagram of an FRC that we looked at on the previous slide. So in terms of similarities between these two, you can see that we have these closed field lines in teal in the plot above me and in black on the FRC plot. And those field lines are what confine the hot plasma in the place that we want it in order to make fusion happen. We then also have a scrape-off layer, which is where we have open field lines that then connect to the wall, and this is what will direct colder plasma out to the diverters, which can then sweep away the colder plasma. So in the case of the plot above me, you can see the diverter that moves kind of out towards the end of the device there, and then the diverters aren't shown in the FRC picture, but the open field lines that move kind of outside of the frame of view will then end on the diverter plates. Additionally, we have a toroidal current in both of these concepts that generates the colloidal field. So again, that's the field that creates these closed field lines, which improves the confinement. In the case of a tokamak, that's driven typically by a central solenoid that creates an electric field around the long way of the donut in the plasma. In the FRC, there are other ways because we don't have a central solenoid in an FRC to drive that toroidal current. In terms of differences, the FRC does not have a strong toroidal field in contrast to the tokamak. This is because we don't have, again, that central column that can allow us to fit toroidal magnets in. And that toroidal field in an FRC is self-generated. It's generated by the plasma itself rather than by external magnets. And this leads to a high value of beta. Beta is one metric that we use to assess the performance of fusion reactors that measures the ratio of the pressure in the plasma to the strength of the magnetic field applied to it. So FRCs are part of a class of what we call high beta concepts. Again, there's no central column in FRCs. Another advantage of this is that it makes them easier and less expensive to build and maintain, especially in certain tokamaks. The central column can be very compact, which makes it very difficult to repair these devices if there ends up being a problem in the central column. FRCs are also embedded in a mirror field, which means that the connection between the FRC and the diverter is simply connected. Basically, this just means that it's much easier to handle diverter problems, to handle the high plasma temperature that will be impacting diverter plates compared to what you have in a tokamak, where you have an annular diverter cross-section. There are many aspects of FRC stability that we can talk about. One of the primary ones is the tilt instability. So if you look at the magnetic field configuration of an FRC, it basically looks like what's shown in the top right of the slide. So you have a bar magnet whose magnetic field points in one direction, embedded in a magnetic field pointing in the opposite direction. And you can imagine that if you had this set up on the tabletop, that bar magnet will want to twist. It'll want to basically rotate around so that its magnetic field aligns with the magnetic field that it's embedded in. And the same effect happens in FRCs if we don't stabilize them. So essentially what this looks like is the FRC itself tilting over. You can see on this flux surface plot on the bottom right of the slide, the two kind of lobes in this cross-section of the FRC sliding past each other, again, to align the reverse field on axis with the normal field off axis. This can be stabilized using FLR or finite Larmor radius effects, which kind of allow a large particle gyro radius to prevent the plasma from slipping past itself like this. And it can also be stabilized using different FRC shaping techniques. So if you make the FRC kind of wider, more oblate, that tends to stabilize the FRC compared to more prolate or compact FRCs, radially speaking. The presence of a significant cast ion population has also been found to be stabilizing towards this instability. This is the approach that TAE and even Helion take in stabilizing their FRCs, is you have a high energy ion population that again has a large finite Larmor radius that then prevents the FRC from slipping past and stuff like this. There are also rotational modes that appear in FRCs that are named based on their toroidal mode numbers. You can see an example of an n=1 instability and an n=2 stability, instability on the bottom of the slide. Typically, we stabilize these rotational modes using multipole fields, and we can also control the plasma rotation, which tends to be an exciting attribute, or an exciting phenomenon for these instabilities using edge biasing, which is basically inducing an electric field on the edge of the FRC to speed up or slow down its rotation. This is how TAE approaches edge biasing. Again, they have on their diverter plates a set of bias electrodes that create a radial electric field around their FRC that can, again, speed up or slow down the rotation that excites these rotational modes. So we've talked a lot about already some of the companies using FRCs to try to build a fusion reactor. C2W is the device that is currently worked on by TAE Technologies. The FRC that they form, again, is created using collisional merging, so they form two smaller FRCs that then collide in the middle to form a bigger FRC, which is then sustained using neutral beam injection. Neutral beams create high energy particles in the plasma that, again, prevent tilting and also heat it up. They can stabilize different modes in the plasma, again, using N-bias electrodes. This is also one of the oldest fusion companies, founded in 1998. And their focus is on aneutronic or PB11 fusion, which we'll talk about in a later lecture. So here's a quick video kind of describing their approach. Another company using the FRC concept is Helion Energy. Their Polaris device is currently being operated, and their next device is currently being designed. Theirs is a pulsed FRC compared to TAE's approach. So Helion doesn't have any neutral beams or edge biasing used to sustain the stability of the plasma. Instead, they try to harvest as much energy from the plasma while it exists, and then as it dies naturally through instabilities, they then create another pulse that they can get more energy from again. They use a magnetic compression approach in order to heat up the FRC using strong magnets outside the plasma, and then they also capture the energy from the plasma using mutual inductance with coils outside the plasma, using what's called a direct energy conversion approach, which can be more efficient than traditional methods for harvesting energy from fusion plasmas. A final company that we'll talk about briefly is General Fusion. General Fusion isn't making an FRC per se, but they are making something that's called a sphere mech. This is like an FRC, but it does have a toroidal field in contrast with FRCs. That being said, it's not created using the central column, the central solenoid that's used in tokamaks. In the case of General Fusion, they're actually using pistons to mechanically compress the plasma that fusion is occurring in order to heat it up and improve the conditions to get more fusion energy. We also have built a handheld FRC here at the lab that we affectionately call CHAD, the Columbia Handheld Academic Device. This is a class of plasma devices called plasma toroids that use inductively coupled FRCs or inductively coupled coils to the plasma in order to maintain the toroidal current that maintains the colloidal field that confines the plasma. There are lots of examples that you can find online of people building these devices, but we've linked one here that we can watch briefly to just show what this small plasma toroid looks like. So one question that you might have or might not have while thinking about these concepts, while learning about the different confinement methods that we've discussed, is why donuts? So you might have noticed that the tokamak, the stellarator, the FRC, there are even other concepts, the spheromak, in the case of General Fusion's approach, are all shaped like donuts. And why do we end up kind of converging on this one topology for creating fusion devices? And the answer to that is hedgehogs, funnily enough. So to explain what I mean, there is this concept in math called the hedgehog theorem, which basically says that imagine you have a hedgehog. If you tried brushing all the spines on the spiny hedgehog in one direction, you'd always end up with at least one cowlick, or one point where all of those spines either converge, they come together, or they diverge. And you can see that kind of mocked up on this sphere here, which you can see has a bunch of little lines on it. If you try to comb all of those lines in one direction, you'll always end up with these kind of divergences, these points where the lines all come together but go apart. Topologically, you can avoid this by, rather than having a spherical or hedgehog-shaped object, if you have a toroidal object, so a donut-shaped object. When your object is shaped like a donut, if you have all these spines on your donut, you actually can code them all in one direction without getting these divergences or convergences. And you can see that again in the far right of the slide. You can see a donut with all of these spines coded in one direction. You can see that they all kind of nicely, smoothly flow in the direction that you want. So taking this analogy to plasma physics, if we imagine that all of these little lines are the magnetic field lines in the plasma, if you have a spherically shaped device, you'll always end up with these points where the magnetic field lines either come together or spread apart. And if you're a little charged particle in a plasma going along magnetic field lines, as you do, at those points, you'll tend to leave the surface of your device. You'll tend to leak out of the sphere. Whereas if you're in a torus, where all these lines are kind of nicely coded in the same direction, there'll never be a point where you leave the magnetic field surface. You'll always stick along those magnetic field lines as they go around the surface of the torus. So this is why in plasma, we tend to end up with devices that are shaped like toruses or donuts. So one final way that we'll talk about for creating a fusion reactor kind of falls under a bit of a different category. It's not magnetic confinement fusion, it's dubbed inertial confinement fusion. Essentially, this is unconfined fusion, though. It's using the approach of high NT, so high plasma pressure, without really caring about the confinement time, and just relying on the fact that you have such a high pressure that you get so much energy out of your reaction that you don't need to actually confine your plasma for too long. So the National Emission Facility is one lab in the United States that has achieved high plasma performance, high fusion performance using this approach. They have achieved what we call Q greater than 1, which means that there's more energy being produced from the fusion reaction than there is going into the fusion reaction. The way that they measure this Q, though, is not consistent with kind of an actual device, because they don't take into account the amount of energy that goes into the full system that creates their concept. However, it is a great scientific achievement to show that we are able to achieve plasma conditions that produce more energy from these fusion reactions than we actually direct into the plasma from the lasers that are used to confine the plasma. So again, in the case of magnetic confinement devices, we achieve a high triple product and a high anti-tau using magnetic fields to increase the tau. In inertial confinement or unconfined approaches, they instead focus on increasing NT. And the way that they do that in the case of the National Emission Facility is they heat up the plasma, so they increase the capital T in NT-tau using a bunch of lasers, 192 lasers. And in the chamber that they use to create their plasma, they have what's called a holoron that holds their fuel for their fusion reaction in a very kind of compact region that when you shine a bunch of lasers onto that compact fuel cell, heats up the plasma, or heats up the fuel, turns it into a plasma, and then achieves hot enough conditions that you produce energy from the fusion reaction that takes place in your fuels that you can then harvest and use to run the next pulse of your lasers. In order to make an actual fusion reactor from this, this would need to happen at least basically once a second in order to, again, produce energy at the rate that you would need not only to sustain the future reactions, the future pulses, but also to then produce enough usable energy out of the reactor. However, there are still companies, for example, Marvel Fusion, that are using this approach, this inertial confinement fusion approach, in order to achieve a fusion reactor. In the case of Marvel Fusion, this is a partnership between a German company and Colorado State University, and they're proposing a fusion reactor essentially based off the NIF, the National Emission Facility design. There are kind of scant details, at least at the moment, about how they plan to capture their energy and achieve the target of 1 reaction per second. However, it's still interesting to see these companies that are using all these various approaches in order to try to achieve a fusion reactor.